Hello embedded learners. Today again I've come with a video series on embedded basics. In the last video, we spoke about basics of embedded on microcontroller, difference between microcontroller and microprocessor, architecture of the embedded system. Hello, I'm Geeta. I work as a technical director for ARM Software Tools. In today's video, we will be talking about in-depth features of microcontroller, what are its basic core components. We'll just touch base upon the peripherals and we'll see what is sensors and actuators, and we will demystify the analog and digital signals. Now let's get deep into microcontroller basics. So now I want to just quickly show the MCU block. What are the components of the MCU? So here in the slide, what I'm presenting, here you can see microcontroller, basically MCU, and it has been interfaced to all these components. So it can be ADC, clock, your memory, main CPU, which goes as part of this microcontroller. We have ROM, we have input output, and we have DAC. So we will be talking about these specific peripherals, some specific peripherals we will select and we will discuss more in this video. So basically the same, I put it in the block diagram for the better understanding of the learners. So this is your MCU block where you have your CPU, because MCU also has a CPU, as I highlighted in the previous video. This is on-chip ROM, which stores all the instructions which the CPU has to execute based on whatever external events it gets. On-chip RAM, you can see it's dual-side communication, because CPU accesses the RAM for reading the data and writing the data to the memory. And we have all these peripherals. So what is this bus? This is called bus. Bus is basically a set of parallel lines which the processor, and I use processor, please take it as CPU, which the CPU will use to interchange the information between the various blocks of the microcontroller. Basically, it carries information. Suppose if the CPU is fetching some instructions from the flash or ROM, it carries the information about that instruction. If it is accessing the memory, RAM, it will carry the data which the CPU is specific to read or it is specific to write. And this bus is, as you can see, you are connecting to all the components of the MCU. So now let's talk about some of the peripherals. So what are these peripherals? Before jumping into peripherals, I would like to tell what is a register, because when you open the hood of the MCU, you will be seeing registers. You will be seeing the peripherals and the clock circuitry which is required to clock the MCU. So what is this registers? Registers are the way to program and configure the peripherals. As I said in the previous video here, first video, that embedded devices are being designed to perform some specific dedicated task. And these are the peripherals which play the key role there. So we have to program these peripherals. So how do you program these peripherals? It is through registers. Each peripheral has a dedicated set of registers. Depending on the peripheral, it can have control register, it can have status registers, initialization registers, everything. So for detailed information, you can refer to the architecture of the MCU, what you plan to use it for your embedded system development. So these registers are key vital role for programming all the peripherals, as I said. So now if you see timer or counter, timer, as everyone know, is used for if you want to count some instruction cycles, or you want to generate some delay in your program, you want to delay the processor execution for some milliseconds or microseconds, then timers can be used. Yes, you can still generate the delay through software, but because the architecture or the MCU already has a timer, so that will give a precise and perfect required delay. Suppose I want a delay in delaying execution of the processor for 1 millisecond or 1 microsecond, I can program the timer in the counter mode, and depending on the architecture, you can configure it as a 8-bit timer or a 16-bit timer. I'll come to this. We'll demystify 8-bit and 16-bit in the next slide. So that specific timer can be configured to as in auto reload mode or an overflow mode, and that can be used for generating the delay. Or you can use this block for generating any pulse width modulator signal. So serial port, as everyone know, it's for transmitting and receiving the data serially. It's a serial data which basically to communicate between two devices. Suppose you have designed two different embedded systems and you want to communicate from this system to this system. So there are various ways. There are various peripherals the MCUs can use to communicate. So in that, serial port is also one peripheral through which you can communicate between two devices. Next comes the IO port, GPIO, which we'll be discussing in detail in this video. So just to quickly tell what an IO is, as the name suggests, it's an input and output port. This is the way how the microcontroller communicates to the external world, is through this GPIO block. Then we have bus control, which will manage all this bus control functionalities inside the microcontroller. We have something called as interrupt controller. In any embedded systems, interrupt control block plays a very vital role. So this interrupt is usually connected to the CPU, sometimes based on the architecture through IO ports. So when I talk about the GPIO example, I'll be demonstrating also to you how the interrupts are also configured, how the CPU will interact with the interrupts. If you want more details on how the interrupts can be configured, please refer to my video on debugging the exceptions in Cortex-M, where I have taken the example of Cortex-M architecture, basically M3, which is a 32-bit core from ARM. So now we will see what's a GPIO programming can be done. So before that, I would like to talk about the registers. Just I was telling, each peripheral has a dedicated register, and depending on the architecture, each peripheral, they can reserve some 4 KB, 16 KB of memory, where this specific memory is used to store all the registers. We call it as special function registers, or they're usually called as memory map registers. Means in the architecture, depending on what microcontroller you are using, they can have the set of registers based on what peripheral you want to program. Suppose if you come to timer, in the timer register, you need to have initialization register for that, control register for that, and if it generates the interrupt. So depending on what is the functionality of the timer, how we want to configure the timer block, that we have the registers. I've just taken an example here. This is a TCON register. Here I've taken an example of an 8-bit 8051 microcontroller. So now before going into timers and explaining the registers, I would like to quickly touch base upon 8-bit, 16 and 32-bit. I believe many of the learners would be having this confusion in their mind. Which one should I go for? So to help you quickly on selecting which particular microcontroller, so the selection of the microcontroller mainly depends on what is that you are expecting from your embedded system. So I did discuss about what is that you have to expect from an embedded system, how you have to design this embedded development life cycle in my first video on basics of embedded. So first, when you're designing your embedded system, you should be very clear what is your expectations from that embedded systems. What is that you're expecting that system to perform finally. So not all the embedded systems need to be higher end. It can be like smartphones, smart gadgets and all. But it can be like if you go for a lower end, just for configuration of LED, controlling the LED, or some traffic light controller, you don't require 16-bit, 32-bit. You can easily do it with 8. So the selection again depends on what is the final output, of course the cost involved, and how well you can use even 8-bit or 16-bit to get that required output. So just to demystify what is 8-bit, 16-bit and 32-bit, this word 8, 16, 32 is associated with the data bus width of the microcontroller. If I take example of 8051, so we have 16-bit address lines and 8 data lines. So 8051 is called as 8-bit microcontroller because it has 8-bit data lines. And ALU, which is part of the CPU, arithmetic logic unit, also perform on 8-bit. So because it's 8-bit is a lower end microcontroller and still you can use it for lower end applications where you're looking to develop a cost effective applications or the application which consume low power, you still go with 8-bit. But performance wise, if you want some high-speed read information like sensors or something where the data has to quickly be captured and quickly processed by the microcontroller and give it to the outside world, then depending on what speed you want the sensors to capture the information, you can go with 16-bit or 32-bit because as you proceed, you will have a good CPU operating frequency as well. So in this video, I'll be also talking about sensors and actuators. So this is just to give an example. Depending on the processor operating speed and depending on your application requirement or how the system has to perform, you can set it any of these devices. So now I'll just quickly go to this registers. Let me come back to the timer configuration register. So this I've taken example of 8-bit, which is 8051. My intention of this slide is just to show you how the registers are used to configure a peripheral, how it is easy to configure a peripheral. When we tell we are programming an embedded system, we are programming the CPU, microcontroller itself. So through which how we'll write the software for that. So in the software, we will be configuring these registers. So basically this is first bit is for timer, which is for interrupt enabling of the for that particular timer, because this TCON register is for both timer 0 and timer 1. 8051 has 2 timers. So this particular register is for 2 timers. This is for timer 0, this is for enabling the interrupt for the timer 0, this is for 1, and these are the control flags for the timer. TR0 is if you want to run timer 1 separately, timer 2 separately. 8-bit, the beauty of 8-bit microcontroller, especially 8051, it is bit addressable. The advantage of using bit addressable is each bit, like in my program, instead of initializing TCON, say AA of 55, I just want to configure only timer 0, or I just want to configure only timer 1. Then I can only play with these bits. I can directly write in my program TR0 is equal to 1 if it is a C program, or if it is an 8051 assembly, I'll write it as set bit TR0. So similarly, we have for overflow flags, TF0, TF1. So what are these overflow flags? I know this is all for the learners, this may be new, but for those who are a bit advanced in embedded, it is a repetition, reiteration. So please bear with me. This is a basic video series which I'm in the process of doing it. So this overflow flags is watched by the microcontroller whenever the timer generates the interrupt. Whenever this overflow flags is set, timer generates an interrupt, and that interrupt can be used as a delay, which I was talking in the previous slide, whenever we want a processor execution with some delay. So here, since I've taken the example of 8051, this is 8-bit register. Like if you go for a 16-bit microcontroller, like you have Infineon series, XE166, ST10, you have PIC18 microchip, which is 16-bit. You have DSPIC24, which is again 16-bit. I'm just naming few. Suppose if you go for 32-bit microcontroller, the registers will be 32-bit. So as and when you go higher end 16-bit, 32-bit, the bit addressable feature of the registers, for some registers, will be disabled by the architecture. When I mean architecture, who is developing that instruction set architecture or the core. If I talk about ARM will be designing their own ARM core. So they will decide what registers should be bit addressable, what will be like you have to access the entire 32-bit registers. So this is about register. I've just taken an example of timer. But if you want to go for other peripherals, they'll have again different set of registers. If you talk about ADC, if you talk about UART. So UART, if you go, for example, you have to set the baud rate generator, you have to enable the UART, then you have this setting this parity bits and all, based on what the UART configuration you want. So next we will go to this GPIO programming. So coming to GPIO is general purpose input output. And before going to GPIO, I just want to give an analogy of how MCU is for the basic learners to understand. It's like MCU, we can take it as a smart kitchen, and registers as the recipe notes, and oven as a timer, and your GPIO as a door, just to make it understand and get that information seeded in your brain. So now let's talk about GPIO, which is part of this video. Why GPIO? Because many of the peripherals of the MCU can be configured, can be accessed through GPIO. So if you take an example, like probably 8051, higher end 8051 if I take, which is again 8-bit microcontroller, but now 8051 is also getting advanced. There, some of the GPIO pins of the microcontroller are multiplexed, are merged with functionalities of other peripherals. Like GPIO can be merged with external interrupt pin, it can be merged with timer pin, it can be merged with ADC pin. So the configuration or how you initialize the peripheral is everything is done through GPIO. So we talk more about GPIO in this video. So GPIO is general purpose input and output. As I already highlighted, it is the way the microcontroller communicates with the outside world. So input, as I suggested, it just takes the input from the outside world, processes it and give it to the output in a layman language. But if I come to the embedded part, input can be, I can connect it to the key or a switch, and output I can connect it to some motor to drive the motor or to blink or to glow some LED, depending on the whatever the requirement you want from the embedded system. So for suppose I have connected the GPIO of my microcontroller to some of the switches or keyboard, then what are the registers which I should configure for GPIO? So now I'll show you GPIO how to configure in Keil software, because I'll be showing on configuring the GPIO on 32-bit microcontroller. You may ask me the reason why 32-bit, because 32-bit I've selected ARM here because ARM is being now many of the devices, embedded devices from lower end to higher end are being powered by ARM. And I would also encourage the learners to start working with ARM, if not immediately, later on the advanced stage, start working on the ARM. So now let me just quickly come to Keil IDE. So here you may be seeing here I have written the program in assembly. So before explaining this program, just let me take 2 minutes to explain what is an assembly is, because I have seen the learners or even the current programmers tend to write the program in C. But they always forget that when they're writing the programming in C, they will lose the actual control on the MCU. Because when I'm writing the program in C, whatever the interpreter or the software compiler is the one which compile your C code to the low level code. So I'll tell you what a low level code is. Processor, when it comes CPU, it only understands zeros and ones. So whatever instruction I've given, move R3, #1000, it doesn't understand anything of it. I'm pretty sure if you have worked on 8086, 8051 in your colleges or earlier, got an opportunity to work on that. We used to have electronics lab or something where we were supposed to run some programs on the trainer kit, which has all the processor, all the blocks like memories and everything, whatever is required. So there, if you remember, we used to feed in the opcodes. What are opcodes? It is, suppose if it's 8051, we will have an opcode of 8-bit. So similarly for ARM, you have an opcode of 32-bit. So that opcode we used to feed in. Where used to feed in? In the program memory. So what used to do? In the trainer kit, when the sign-on comes, enter the address of the program memory and start feeding in, loading in those opcodes. And when you give a reset, processor used to fetch those opcodes from that memory and start executing, because processor understands those opcodes. Then the architecture is defined. Suppose 8051 means based on the opcode, that 8051 processor will operate accordingly. Suppose if the opcode is for move A, B register, moving the contents of B register to A, or moving the contents of gen purpose registers R0 to A. So what do you mean by gen purpose registers? These registers are something out of peripherals. Peripherals has a dedicated registers, whereas gen purpose registers are used by the processor itself to perform its internal functionalities. 8051 8-bit has again 8-bit registers, R0 to R7. ARM has R0 to R15, is again 16 registers, but all are 32-bit. So let's talk about the assembly instruction here. So any code you write, it's a C program or any high-level language code you write, processor only understands zeros and ones, what we call it as opcodes. So here these instructions are nothing but we call it as mnemonics. The reason I have written this program in assembly to show you in this video is through assembly one can easily control the microcontroller. you have a complete grip on the processor itself, and you can make the way you want the processor to operate. You can modify its flow as you want it. So assembly instruction is always important to, and suppose if one user has an information on assembly instructions, it's like added advantage, I can tell, because some of the peripherals of the microcontroller we can still programming in C, but when you want to generate some delay or some critical operations, like in microcontrollers you have no operation, that instruction execution also there is some delay. Suppose if you want to include that in your C program, wherever delay is required, assembly instruction is the best way. That's the essence of assembly instruction. Assembly gives you good control on the microcontroller. So using assembly instructions, you can program anything. You can program interrupt, you can program peripherals. Only you need to know the instructions. So now coming to the GPIO part. So in this program, I am using LPC1768, the same processor which I took in my video on debugging exceptions in Cortex-M. So here, when you come to GPIO, first thing is you have to configure that GPIO block. For some of the microcontrollers, the GPIO block is by default powered. Sometimes what happens now, modern electronics require that, though as I said, it's like a system on chip. Many peripherals are coming onto the microcontroller. So it's becoming as a system on chip. Means they're building an entire system, high-end embedded system on a chip. But not all the peripherals are powered on. Just to ensure, when you give preset to the particular processor or an SoC, to ensure that overall power consumption is kept minimum, not all the peripherals are being powered. But GPIO is default usually powered up by the processor. But that you have to get it from the architecture datasheet, whatever architecture datasheet you are using it. So in the GPIO, here we have, first thing is configuration. First to check whether the GPIO block is powered or not. Next to see whether it is clocked or not, whether the clock is coming. Because when we say that buses is used to transmit the data from one block to another or from GPIO block to the CPU, the data is passed through the buses, but it is passed in clocks. For each clock cycle, for every clock tick, clock whatever, it can be oscillator. It's altogether again a different topic here, but so this data is being transmitted between the components of this MCU with the help of the clock. So first we have to see whether it is powered, it is clocked correctly, and then we have a direction register, because as it is input and output. So this direction register will tell me whether I am configured it as an input or output. So in my program, all the bits are output. Okay, because it's an ARM I have taken. ARM is a RISC architecture. So there is a dedicated register set for even for clearing the bits of the port and setting the bits of the port. Say suppose I have configured a particular GPIO pin as input. Then I use the FIO pin register to read the data. Pin register is, suppose I have pressed any key, the GPIO pin is connected to a specific key or a button. Then when I press that button or a key, that pin will sense that data and it will give it to microcontroller. To read that information from the port pin, you have to use the FIO pin register. And please remember, these all the registers I'm talking about specific to ARM. Okay. But for 8051, if I come to 8051 architecture, reading of the, even if you read the data from particular port pins, you'll be reading it through register only, directly. P0, P1, P2, P3 like that. But here in ARM, there is a dedicated register for it. Suppose I'm configuring the IO pin as output. Then I send the data to it through FIO set. Okay. So that is how port registers, these are the registers, like in this case, direction, clear and set. These are the registers which I am using in my ARM Cortex-M microcontroller to program the GPIO. So this is how it is easy to configure the GPIO. So when we write, we are telling that we are doing embedded programming. It's just we are programming the peripherals. So how the programming is done? Through registers. What registers? Special function registers. So this is how I have written the code for Cortex-M. So now I'll try to just test in the simulation. So simulation is a virtual target basically. I'm not connecting any hardware board, or I don't have any embedded system connected to my laptop. It's just some of the softwares like MDK gives that feature where you can, without connecting your hardware also, embedded system also, you can test your code. This feature will certainly help you when you are at the early stage of developing your embedded system, which will help you to test your code, actually how it works when your board is ready or your device is ready. So now here GPIO, I have opened this block from peripherals GPIO interface. So there are 5 ports in LPC1768. Now let's go to my program. So here, as soon as I enter the simulation, there are some many things to observe. Note here, registers, you can see all the registers are not to R15. These are all, we have 16 gen purpose registers, but all are 32-bit registers here again. And there are some mode registers, because Cortex-M operates in different various modes, which we are not getting into this, which is not part of this video. But if you want to get more information on this, please refer to my video on debugging on exceptions, where I have explained about these different modes of execution in Cortex-M. So now you can see these gen purpose registers. As I said, they are not part of peripheral blocks, or these not registers are used for peripheral initialization. This is just for moving the data from here and there, from memory to the register and writing to the memory. Because ARM is a load store architecture, means it directly cannot write to the memory, similar to 8051. 8051 also, the controller cannot directly write to the memory. When you want to update, modify the memory, you have to read the contents to a register, modify it, and then write back. So here also it's read, modify, write. Same concept is extended for 32-bit ARM as well. So these registers will help you in moving your data from memory to the processor and processor to the memory. So here R0, here first I'm giving the value direction register. So here I'm using some of the port pins. These, because this particular project is developed for 1768, which is Cortex-M3 processor. So there is a board also developed by ARM for that, and this code has been written for that specific board. So here for some of the port 1 pins is what I'm configuring it as output, and if I load this code on the board, it will continuously blink the LEDs on and off, because these pins are being connected to the LEDs as an output. So these pins are configured as output. Right. So now FIO1 DIR, this is the address of the register. So as I said when explaining about the registers associated with peripherals are memory mapped, right? Because FIO1 DIR is the name given by the silicon manufacturer here, who is the PC1768 NXP. But this FIO1 DIR, ARM processor will not understand. So this particular register is given specific address, and that address I am loading to R0. So I am using R0 as a pointer to that address. So after that, I am loading R2B00. So this is the, for configuring the bits of port 1 as output, I am using this value. That's that I am loading to R2. Then I am storing the R2 to R0, means the contents R2, which is that configuring some specific bits port as output, that I am loading to R0, means R0 is pointing to that register. So this specific instruction is nothing but I am loading the value B followed by 7 zeros to the direction register. So this I would not be able to explain if I write it in C. So that was the reason, because and this is about learning the basics of embedded. So I thought, why not explain in assembly. Next, similarly, so this is a loop here. This is a delay R0 preloaded with some delay value, so that you can observe when you actually load the code, when you download the code to the flash of the microcontroller, when you give the power on reset, when you give the power to the board, the processor executes the code and it will show the LED on and off. For a human eye to note that difference of on and off, the delay is being provided. So similarly, FIO1 clear is in address, some specific address. There also I am writing B followed by 7 zeros. So you may ask, direction also you wrote that value and clear also, because I said ARM is a RISC architecture. If you want to clear a specific bit of the port, some specific port pins also, port bits also, I have to write it to the clear register. I cannot directly write like 0 0 and it will be that particular pin will go low. It's not correct. That is not applicable for ARM. So there is a dedicated registers for even the clearing the port bits and for setting the port bits. For setting the port bits, I'm using F501 set. Then my actual program starts from here. I'm just executing the instructions stepwise one by one to show the learners that how processor executes and how it loads the registers, how we can configure the registers basically. Then this is your delay. So now this is a delay. Now I will do is here I'll put a one breakpoint here, and this is a delay. So this is for setting and this is for clearing. So because why I have put this breakpoint? Breakpoint is a concept. Quickly tell you, though I'll be talking about, try to cover this topic in my next video, which is programming basics. There I'll try to capture this information because this video series is also for advanced embedded, where I may be talking about advanced debugging mechanisms, debugging techniques and features. So certainly I'll touch this particular point there. So breakpoint is something to quickly now for you to understand is whenever I want the processor to stop at specific instructions. Stop in the sense I want to stop the execution of the processor itself. Because there's a delay involved. If I keep executing the instruction step by step, then I'll not be able to show you the changing of the port pins. So now because I put a breakpoint, I'll be able to show you how the pins here, port pins, goes on and off. Means it gets set and it gets cleared. And that's the reason I have put a breakpoint. Now let's run the program. So first is clear and set. So you can see here, the bits are set. This last 4 bits, please watch out. Next again, I put, again you see, the bits are cleared. So this is just to show you this pins is getting high and low. These pins are connected to the LEDs on the board. So it makes the LED go on and off. So this is just a simple program which I have showed on this Cortex-M3 MCU on how GPIO can be configured. But GPIO also have the pins. Some architecture pins may have push-pull, open collector. Depending on GPIO has different modes of how the port pins can be configured. Right. Now let's come back to the presentation part where I'll be talking about sensors and actuators. So before going to the presentation part, just let me give you some theoretical point. So what is sensors and actuators? Sensors are nothing but the way the microcontroller sees, senses. Actuators are something how it acts on the data, whatever the microcontroller sense. So if you take sensors and actuators are nothing but the eyes and hands for your microcontroller. This is how the sensors works. So now coming to sensor, just in this particular slide, now I'm coming to the slide. So here first picture shows the difference between sensor and actuator, and second picture shows what's the real world examples. So in a basic terminology, or just to give an overview on what a sensor in embedded is, it just converts whatever your physical signal into electrical signal. Electrical signal can be, it is usually in the form of a ADC form. What actuators does is it will convert back that ADC or ADC signal or electric signal back to physical signal. This is just in a one line what the sensors and actuators do. But if I take an example for a microcontroller, if I take GPIO for example, so I can connect the sensor to the GPIO, which can mean ADC. GPIO which has a sensor which has an ADC associated with it. And output I can connect it to a GPIO again to a which is configured, that particular port pin is configured as a pulse width modulator signal, PWM signal. So suppose here what it does is sensors. If I take what I said, sensor is actually sense the outside atmosphere. It senses how the microcontroller sees. So suppose if I take a light sensor or a temperature sensor, so that information, that temperature or the light information is fed into the MCU, and output can be this actuators can process the data, and maybe it can turn some servo motor or switch the AC load or turn on some buzzer whose music is controlled through the timer of the microcontroller. To take a real world example quickly, let's take an example of soil moisture sensor. So in this case, the sensor here is nothing but sensor input is through GPIO, which is configured as the ADC, and that sensor will sense the moisture content in the soil. MCU will process that. It will look what is the moisture content of the soil, and then it will turn on the relay which is connected to the PWM output, which in turn will auto water the plant. So this is an example of sensor and actuator, but you can see here many of the examples. Like sensors can be motion sensor, like you put an alarm for your security purpose at home, or if someone passes by, alarm should blow saying that someone has passed to the gate or something, whatever. So like that, we can have sensors, we have actuators, like a burglar alarm, or it can be healthcare related, it can be sensor for monitoring the heart rate, or it can be actuator, where just now I said for pumping the water in case of irrigation where the soil is dry. This is about the sensors and actuators. So in this sensors and actuators, I would like to quickly show an ADC example for the same LPC176 microcontroller which I planned for. So now that just theoretical part, we know what is sensor and actuators and how they differ in operation, and I just gave a real world example. Probably because everywhere we talk about now, sensors are used like an IoT for agriculture, farming and all, to know the quality of the crops, quality of the soil, to based on that they can decide how much they need to get the pesticides or whatever manure, whatever is required for that, improve the quality of the soil. So now let's come to the example of specific to that 1768 board, again Cortex-M3, but in this specific project I'll be talking about ADC, because as I said, in sensors and actuators, sensors are usually connected through GPIO or through ADC, and in my program the ADC is, we are connecting the potentiometer to give an input to the ADC. As you know, ADC is analog to digital converter. So we were giving the potentiometer. So what is a potentiometer? It's a mechanism which we use for an embedded system to give the varying voltages from 0 to whatever is the highest possible. In this device, LPC1768 is a Cortex-M3 microcontroller which operates at 3.3 volts. So here I can give an input from 0 to 3.3 volts. So I'm not going to explain the program in detail here, but I'll be just showing the ADC part quickly on how these ADC registers are configured. Again, here special function registers, ADC control register for enabling the ADC block power and start the ADC conversion. Then after this ADC conversion, once the analog to data is converted to digital, it will generate an interrupt. That is a way it is a signaling to the microcontroller, is signaling to the user that yes, the conversion is complete. Otherwise, the user has to keep polling the specific bits of the register to see whether the conversion is done or not. But in higher end embedded systems, higher end devices, you have interrupts. Basically, I guess I can see that in the lower end devices as well. So with the help of interrupts, you can easily trap the processor when you write a program for interrupt handler, where I have explained in debugging exceptions in Cortex-M3 about the interrupt handlers and all. So once you write that, it will there in that function I can actually read the digital data. So in this case here I can show you ADC. This is the function which will initialize the ADC. So you can see here, as I said, ADC functionality can be multiplexed with the GPIO pins. So only we stress more on the configuration of the GPIO, and that was the reason I took a separate topic as part of this video to discuss about GPIO. Okay, now in IRQ file, okay, so there is a separate functions here I have written for starting the conversion, stopping the conversion, starting the analog to digital conversion, and once the interrupt is hit, to stop the conversion, then get the converted value. So here I have defined a macro just for the part of this program. So if this macro is defined, then we are enabling the interrupt for the ADC. Yeah, until we enable the interrupt, processor will not recognize the interrupt. Okay. So after reading this, it will read the data, and here in this main function, I'm just continuously in the while of one infinite loop, I'm just continuously reading the digital data, and I am displaying on the serial window or on the display. If you are planning to have a display LCD on the device, embedded board or embedded device, then you can display there to show, because it's a sample project for that specific board. So this is how we have given. Now let me So now in this application, in this demonstration, I'm open two windows like GPIO to show that LED is blinking and ADC. So you may ask me why ADC and GPIO? Because the sample project which is provided by ARM for that board includes when you rotate the potentiometer, when you vary that potentiometer, that analog value is converted to digital, and that digital value is given as a delay for blinking of these LEDs, right? So now you may ask me, oh, you are running the code in simulation. How are you giving input to the ADC? That's the beauty of Keil simulator. There is a concept, something called as signal functions. So probably I'll make this video for programming basics, but to just now, signal functions is basically runs in the background, because in your simulation part, the foreground, your main application executes. Signal function executes in the background of your application. And signal functions is like a similar C functions what you write. But here the signal function will generate a signal, can be a triangular wave, sawtooth wave, square wave, sinusoidal wave, any signal we can generate through C code. That's the beauty. So through C code you can generate that, and you can feed into the ADC. Now next question you may ask me. So Geeta, you were talking about ADC pins which are part of GPIO, which are nothing but the pins of the MCU. Then in my C program, how will I feed in the input to the pins of the MCU? Is it possible? Well, actual programming in C may not be possible, but with the help of signal functions and the features, simulation features what Keil has provided, ARM has provided in the MDK software, you can do that. Appreciate that feature. So I'll show you what is that signal function. Well, this is my signal function. So you can see it's a simple C function. Only thing is, you should not pass any parameters, so it should be void. You should not return any value, void. Parameters can be still passed. So in this function, I'm generating a step wave, which is a step wave, which step is 0.1. I'm writing a C program which will increment this volts in 0.1, where the limit is 3.3. As I said, this 1768 is 3.3 volts compatible, because NXP is a low pass CMOS controller. And then there is a delay. So what is this delay? Delay is because now in my Keil IDE simulator, there are two codes executing. One is background, this is my signal function, and foreground, my main application code. So this delay will help the IDE to switch between both the modes, signal function and the main function. So limit is 3.3. So from 0 it starts incrementing 0.1, 0.1, 0.1, go to 3.3. Again, once it reaches 3.3, again decrement by 0.1 and come to 0. So this repeats in infinite time, while of 1 means without stopping and infinitely, countlessly, it will keep executing this code. Okay. Unlike in C function, until the function is called, processor will not go to that particular function. So here in this case also, until we call the function, the signal function will not be executed. So signal function starts with the keyword signal. This is very important. So here I'm invoking the signal function with 3.3. This is a limit. So I'm telling this ADC on this particular device has a maximum range of limit of 3.3 volts. That's it. There is a compile here to check if there is any syntax error, and you're done. Okay. So now in my program, I'll show you how ADC works. So I'm feeding in the analog input through the ADC of the controller, and you can see here the input, whatever I'm feeding, analog input, as well as the results, digital data. Because this ADC part I have already defined it. Right now, let's go. So you can see here AI in 0 is incrementing in steps of 0.1 because I am feeding, you can see here, this is the logic analyzer, which is again a feature of Keil simulator. This will show you what is the analog input you have fed into the ADC. Since I said it's a staircase waveform, so it goes up to 3.3 and comes to 0, again it goes to 3.3. So you can see here, this is the input range which is been set, and based on that you can see the result 2. Means AIN2 means it has a result 2 register. Similarly, if it is AIN7, there is a dedicated result 7 register. So this specific application, you can see how ADC can be configured even before your device is ready. So that is the beauty and one of the feature of Keil simulator. Now let's come to the last topic of this video, demystifying analog and digital signal. Now that we have seen how the sensors work, though this is not an actual sensor, but because sensors are also parts connected to the ADC, and here I have showed how the potentiometer can be connected to your device through ADC, and it can give the analog input or it can give any sort of input to the ADC, and I have shown how it works in the simulation. Now let's come to the last part of this video, understanding analog to digital. What is the difference between analog signal and digital signal? So what does this analog signal or digital signal means? Why does not microcontroller sometimes able to see the smooth curves which is coming to the pins of its MCU? So let's demystify analog and digital signal. So analog and digital signal is very simple to understand. In just 2 lines I can explain you. Analog signal is a continuous signal, means there is a range. For example, if I am trying to work on an analog application for 8051, 8051 operates at 5 volts, 0 to 5 volts. So I can feed in any signal to the device, to the microcontroller from 0 to 5 volts. So it's a varying signal from 0 to 5. 0, 0.1, 1, 2, 3, 3.3, whatever. So it's a continuous signal. It can be sine or audio. It's a continuous signal ranging from 0 to the highest range. In other words, for the digital, it is a discrete waveform. So either it can have value 0 or it can have the value 1. So if I take example of 8051, 0 volts is the 0 value and 5 volts will be my value 1. So let me just quickly show you the diagram of this analog to digital signal. So you can see here, analog signal is a sinusoidal wave. It's a continuous varying signal. But digital signal, at any point of time, it can be either low or it can be high. There is no intermediate value for it at all, right? So if you come to the microcontroller world, you come to the embedded systems with microcontroller. Entire microcontroller application, embedded systems work with digital form only. Digital signal. Where does analog required? Whenever there is a requirement of analog, like in sensors or wherever, analog signal analysis or processing is required. Usually microcontrollers tend to use the ADC block, peripheral, which is part of the controller, or if the controller doesn't have the ADC, it can be connected externally, interface to the controller externally. ADC externally is also possible. So that is how analog and digital signals vary. So now coming to, now that in this video we have covered all the topics which we plan to, basically on microcontrollers, its basics, its core components. So congratulations, you are now grasped the MCUs on how its core is being designed, implemented to the real world interfacing. And we also covered in this video the heart of the embedded system, or the main brain of the embedded system, which is nothing but the microcontroller and its inside blocks, magic of GPIO, and how sensors and actuators work in combination. And we covered some of the signal basics, which is analog and digital. So now the next step I would request the learners is grab an Arduino board, blink an LED, configure an LED, include the sensor on it and build on it. practice makes pro. Next, I would suggest you can build a traffic light controller where the LEDs are connected and the delay is controlled through timers. And for the advantage of this, I would like the learners to request use MDK software for ARM if at all planning to use ARM, or the DS software, because we also have Keil software for 8051 if you are planning to develop for 8051 MCU. So you can still use this software to develop the programs which will be running, which will be fed into the flash of this embedded systems, and you can get it going. Thank you. I'll be coming with the next video series on programming basics, where I'll try to cover high-level language C and assembly languaging and some of the basic programming skills. Till then, stay tuned. Bye-bye.